Thank you, Jorge, and thanks for inviting me here. It's good to be here. So, what I'm going to talk about is a couple of different works that we did basically on trying to understand urban data and trying to understand the city using data from cities, obviously. So, I'm from New York City, and there's always some development happening, something or the other happening. So what is the big deal about big urban data, right? And so if you look at it, a lot of people are moving into cities. So city is like the center for economic activity, and this was a recent kind of increase in population in cities, and you can see that we are around the 60% mark right now in general, and it's expected to increase to over 70% towards in another couple of decades, right? And increasing amount of people in such a small amount of place is obviously going to lead to a lot of problems, and the hope is that, am I audible? Yeah, okay. And the hope is that somehow by using data from cities, we can actually try and get a better understanding of the cities and be able to frame policies to kind of improve how cities work and, in short, help people, right, the citizens. And there is a lot of data exhaust from cities. So this could be like regarding infrastructure. So this would be like public transport, taxis, at least in New York, there's a city bike or the subways. Or you can have data about environment. So we have data corresponding to weather that's happening and rainfall and how it varies over time and different parts of the city. And you have data from social media, which basically tells about people, the movement of people and how, for example, Flickr talks about where tourists like to go in general. And you have Twitter, where people tweet about anything and everything, right? And a lot of this data is not just being collected, but it's also being made open by many of these cities. So in US alone, there is NYC Open Data. There's one from Seattle, Maryland, Chicago, San Francisco, Los Angeles, a lot of places. But it's not restricted just to the United States. It's also happening in a lot of different countries and also a lot of developing countries. So India has an open data platform, Brazil has one. And I just did a Google search and I found that even Peru has a portal wherein there is some data available from Peru, right? So given the large amount of data that's being collected from the environments, it gives us an opportunity to make the lives of citizens much better by framing more policies, making cities more efficient and sustainable, right? And given this recent trend in a lot of open data, it is therefore not surprising that there has been a lot of work that people are pursuing in understanding urban data sets. And I'm just going to list a few examples here. So you have some work that look at vehicular or traffic movement, or you have work that look at general human mobility, or you have studies on air pollution, on public utility service and how effective it is, and on gentrification. That's basically how a city is growing, in which parts it's becoming much more prominent with lots of development happening, right? And this is just a small gist. There is lots and lots of work where people are tackling different problems arising out of cities using the data from these cities. But if you look at a lot of these solutions, all of them are kind of specific to a particular data set. So the vehicular movement and the kind of techniques that have been proposed are very specific to that data set, right? And they make a lot of assumptions about the data, such as the properties, or if you're looking at interesting events or features in the data, the shape of these events. Like, for example, it is within a circular region, or it is within a rectangular region, and things like that, right? And more often than not, they work with sample data because the actual available data is really, really large. And by using sample data, you lose a lot of information. You miss out on maybe some small kind of feature that is actually very interesting. And because of this, a lot of these techniques are also not scalable. So the goal of the work that we are doing and have been pursuing over the past 2-3 years is primarily, given the setting of having lots of urban data, is there some general way you can quickly get started with the data? So there are domain scientists who are very good at what they do, but given a lot of these new data sets, how do you get started with it, right? So the first question I'm going to try to answer in this talk is basically how to get started when you get a new urban data set, and in a kind of a general way that doesn't require any specialist knowledge from the domain experts, right? They just get the data, they need to be able to plug it in, explore it, get an initial understanding of the data, right? And the second question that I'm going to try answering in this talk is basically, how can we use these multiple data sets that are available and and how do we use that to understand the city, right? And I'll go into details of that later. So for the first part, again, since we are talking about urban data sets, a typical data set which I really, really like is the New York City's taxi data. So how many of you are kind of familiar with this data? Anyone here? Okay, I see 2 or 3 hands here. Fine. So this is a very good example of urban data, and it has all the properties that urban data sets usually have. So what this data is we have from, I think the Taxi and Limousine Commission in New York City has fitted the taxis with GPS and has been collecting data since 2009. And they've also made it available open, right? So there are approximately 175 million trips that happen in a year. And this is the interesting property of any urban data sets, that it has a space component as well as a time component, right? So it is spatio-temporal. And if you consider the taxi data set, it increases that complexity by having 2 spatial attributes and 2 temporal attributes. So here we have, for each trip, we have the pickup location of the trip, where they dropped off, pickup time, and the drop-off time, right? And so this is the New York City's taxi data, but there are other taxi data, say from Beijing, where you also have the exact trajectory of the trip. So I think you have every 5 minutes or every 2 minutes trajectory of the trip, right? And of course, together with that, you also have other regular attributes, such as the fare that was paid for that, the tip, the distance, the duration, and so on. So say you're given a new data set with these properties. How would a domain expert start analyzing these data sets, right? So one of the neat thing, or the easiest thing one can do, is just aggregate the data and plot it over time. And so this is here, what we have done is we have plotted the 2011 and 2012 taxi data and the number of trips that happen every day, right? And of course, this gives us some interesting features immediately. So there are some drops here and some drops here. So these 2 drops in particular correspond to when Hurricane Sandy and Irene hit New York City, right? But if you look at this drop, this is on Christmas. And this is on, again, New Year's Eve or New Year's. So you can see some interesting patterns that happen, but this only gives some sort of a high-level view. Instead, if you actually visualize the data in a much more finer-grained way, you can actually see more interesting patterns. So this is on one particular day. So this is May 1st of 2011. And what we have done is we have plotted all the trips, the pickup and drop-off locations of all the trips from 7 a.m. till 11 a.m. And if you notice, between 8 a.m. and 10 a.m. for that 2 hours, this particular street, which is Fifth Avenue, essentially, is completely blocked, right? So, or rather, there are no taxi trips that happen at all over here, which essentially says that it is blocked. And the reason for this is because there was a 5-borough bike tour that happens every year, and during that time they block all those streets in order to allow the bikes to pass. And therefore you see that you can find this in the data, right? But the problem is, this is like 2 hours over the entire year. How do you find these interesting slices of data where something happens, right? And again, so existing techniques typically for analyzing, like I said, aggregate the data. So if you aggregate it over space, so you just have a time series, you can see that. So here what I'm doing is, this is the aggregate for the, so this fell on a Sunday, May 1st. I take the previous week and the next week. So we have 3 weeks of data. But if you look at between 8 and 10 a.m. over here, you don't see any difference. You cannot find it. Or similarly, if you aggregate instead over time and look at it in space, again, if you look at that region over those 3 days, you don't see any difference, right? So aggregation is really not an option. You really have to look at the data in its fine-grained all details, right? And of course, manual exploration is not an option either. So you literally have to look for every hour in a single year. And if you have multiple years data, identifying these features is not going to help. So our goal is here is, how can we guide users towards potentially interesting data slices? So you're given a new data set that just comes to you, and then I want to understand this data, I want to find interesting parts of this data. So instead of manually doing it, can we somehow semi-automatically do it? Can we somehow guide users saying, okay, these slices are kind of interesting, go have a look. If you don't like it, discard it, right? But then we have to define what is an interesting data slice. So we could say, okay, it contains some sort of an event or interesting feature or interesting pattern. But then we would need to have some sort of a flexible definition of these events. So we needed to have arbitrary structures. So again, if you look at this, this is not any rectangular region or whatever. You have the shape actually goes in some sort of a polyline, right? So you need to have some way of having an arbitrary shaped features in the data. You need to kind of identify it. You need to be able to identify different types of features, right? And it needs to also have on multiple temporal resolutions. And of course, it would be really nice if the user already knows, or the domain expert knows, okay, these are the kind of patterns I'm interested in, to quickly query and search for such patterns, right? So how do we go about doing this? The idea is to look at the shape of this data, and by shape I mean the topology of the data, right? So let me give you an intuition as to what I mean by topology of the data. So let's again start with, this is Manhattan, and this is the density of taxi trips. And so here, white basically says there are very low trips, and as it keeps getting darker, the number of trips is much, much higher, right? Say we can somehow represent this data as a terrain. So in this terrain, it's like for each point in this terrain, the height basically somehow magically maps to the number of taxi trips in this terrain, right? So now, if you have this terrain, and if you look at, say, one of the peaks of this terrain, it basically would correspond to that region over there, which has a very high number of trips that is happening, right? Another peak would correspond to a similar region with, again, high number of taxi trips. And let's look at this region over here, wherein there are no taxi trips, somewhere in between all the really high taxi trip regions. So this would basically correspond to these, this valley over here, right? So we need to somehow magically transform this into terrain. I'll go into that in the next slide. So the simplest thing is just looking at the peaks and valleys of this terrain representing the data, you can identify a lot of these interesting features of the data, right? And this is naturally captured by what we call the critical points of this function, right? And so one of the main advantages of using the topology of the data is that it naturally captures these kind of features, very intuitive features. So let's see how this terrain is formally defined. So basically, as long as the data can be represented as what we call a time-varying scalar function. So it is essentially a function that goes from space cross time to a real value, to a single value here, right? And so basically we want to map each point of a domain, in this case city, some representation of a city, over time to a single function value. And at least over the course of this talk, I'll be using two different representations of the city. So in the first case, we have the road network of the city, in this case again New York City or particularly Manhattan, and for each node of this road network, you can define a function value which would be something like the density of taxis, right? And another representation is to basically have a high resolution grid, and each pixel of the grid corresponds to, again, the density of taxis. So you could have these two representations. So for the first part of my talk, I'll basically be using the road network. So given that we have this way of defining scalar functions, or we have a scalar function that is derived from the data, so this basically gives us the terrain that we want. How do you identify these topological features, right? And like I said, the critical points captures naturally the different features that we are interested in. And so we look at the neighborhood of the critical point. So let's again look at this terrain. The peaks correspond to the maximum or the set of maxima of the function, and the valleys correspond to the set of minima of the functions. And the neighborhood of a maximum or a minimum is basically defined by the actual domain corresponding to the peak. So this whole peak over here I would say is the region corresponding to that maximum, and this whole value over here would be the region corresponding to that minimum, right? So let's take again a concrete example. This is again between 8 and 9 a.m. on May 1st, 2007, when you see that when the bike tour is basically happening over here. So when you convert it into a density function and look at the set of minima and the valleys corresponding to that minima, you actually get this kind of shape over here, which basically says, look, these are two valleys that correspond to this particular region. And you can clearly see that it kind of follows the shape of the bike tour itself. It follows how the tour happens, the way the roads are blocked. So in a way, using this, we can have features that have arbitrary shapes, right? And so how do we go about computing this? And to do that, we use a data structure called the merge tree. So let me again give you a brief kind of intuitive definition of what a merge tree is. So say you again consider this terrain, and say we set a threshold over here, right? And let's look at all points that are above this threshold. So when the threshold is higher than the global maximum, say the threshold is infinity, then there are no components. There are no points that are above the threshold, right? But as soon as it decreases, say to just below the highest peak over here, there is a single component that is formed, right? Let's keep continuously decreasing this threshold. So when the threshold becomes even lower, in this example, there is another peak goes above this threshold, so we have two components. At some point, there's a third component, and at some point, they kind of merge together and become just one component, and as it goes below the global minimum, it remains at one component, right? And let us track the number of components as we keep changing this threshold. So if we do that, what we get is this graph over here, which is essentially a tree, and which we call a merge tree. So there are two types of merge trees of interest here. One is when we vary the threshold from plus infinity to minus infinity and track all the components that are above the threshold. And the other is when we vary the threshold from minus infinity to plus infinity and track all components that are below the threshold. So when you go from plus to minus, basically we track how the maxima are formed and how they get merged. When we go from minus infinity to plus infinity, we track all the minima or the valleys and see where they merge and so on, right? So given this, you can actually compute this merge tree efficiently in O of n log n time, where n is the size of the domain. So given this merge tree, now how do we use this to find the peak? And basically this tree, for each point on the edge, you can actually augment all the regular vertices, that's nodes or points on the domain that are not critical, are associated with any of these edges. So say I want to kind of compute the different features of interest over here, and say I want to find the valley or the domain or the neighborhood of this peak. So I want this whole peak here. How do I do that? I look at the corresponding edge that's incident on that maxima and look at all points corresponding to the maxima, and I get it, right? And this was essentially how we got over here. So we had, again, the merge tree looking at minima, and I look at the edges corresponding to the minima and look at all the nodes of the domain over here that correspond to that, and I actually got this feature. Right, and given that it's just O of n log n, and usually it's much more faster than n log n, so it's really efficient. It's almost linear in time. It's the actual, if there's a very efficient algorithm that does it in O of n plus t log t, where t is the number of critical points. So it's near linear when you have large data sets. And so this gives us a nice way to identify features, but the problem with real data is there is a lot of noise in the data. So even a little bit of noise can create lots of these local small valleys, bumps, and peaks in the data. So we need to somehow take care of this noise for it to be useful. Otherwise, you're going to be inundated with so many features that you cannot make sense of what we need to look at, right? And again, so we need to identify what these important features are. And again, there is this notion of topological persistence, which helps us identify these interesting features. So intuitively, what is persistence, right? So you can think of it as the lifetime of the topological features, or as we keep varying the threshold, right? So this feature was the first to form, if you recall the threshold, if you recall the previous example where we varied the threshold, right? And this was the second to form, and at some point these two would merge into, say at S2, this component merges with this component over here, right? So if you think when a component is created as its birth time, and when it gets merged or destroyed, it's its death time. So you have some notion of a lifetime of each topological feature, and which is essentially what persistence is. So intuitively, it's nothing but the height of a peak or the depth of a valley, right? And you can use this persistence to, persistence can be, again, efficiently computed using the merge tree, once we have the merge tree. And we can actually use this persistence to simplify unimportant features. So for example, we have this peak over here, which is very small, and say it's potentially noise, and I just want to remove this, so I don't want this to clutter our set of features, right? So all I need to do is look at the corresponding edge in the merge tree over here, and by kind of removing the edge, you know the domain that corresponds to the edge, and you can simplify that domain and you can remove it over here. And which ends us with these two high peaks, and we can say, okay, let's look at just these high peaks, right? And again, you can effectively handle noisy data, and it's proven that using persistence, the persistence measure is robust to noise, so we can make use of it. So to summarize, using topology has four main advantages. One is it naturally captures the features, some of the interesting features, not all. And then these features can have arbitrary shapes, you can efficiently do it, and you can handle noise, right? So now, given this, how do we make use of this to guide users to explore any new data set that comes in? So before I go any further, if there are any questions so far, I'll be on. So let me continue. And so here the idea is to use these topological features and point users towards the right parts of the data, right? And the way we do that is, so we build this framework to basically do that, which takes the input data, and then we use the topological concepts that I just described to find what we call a set of micro events, right? So these are essentially all the topological features, all the peaks and valleys that are of interest, right? And from here, we basically create an index that kinds of clusters these micro events into a set of macro events. I'll give you a much more concrete example as to what this is shortly. And then we create this visualization framework, exploration interface, where users can quickly kind of look at points, and it kind of guides points. So for example, here, there is this kind of point that is isolated, lonely, somewhere out there in the right. By just choosing that, you can identify these interesting events, which in this case corresponds to the Fibero bike tour. And if you have some such events of interest, you can also query these events, and using the index, you can almost interactively get results over here, identifying all the other kind of features that have the similar properties as the Fibero bike tour at different times. So let me go through each of these steps a little more in detail now, right? So like I mentioned, using all the high persistent peaks and valleys from the data, we get the set of micro events. And so this is for one time step, and you can see that each component here corresponds to one event. So this is one big component. There are lots of small components all over the place, right? So there are several features or several micro events per time step, and we group all of these within a much larger time interval to represent a set of macro events. So let me take the bike tour example again. So we know that it happened between 8 a.m. and 10 a.m. and if we have time, if you have discretized time into hourly periods, what we get is we get one micro event corresponding to the bike tour at between 8 and 9 a.m. and we have one more between 9 and 10 a.m. So these two would potentially be grouped together and say that, look, this is one big macro event that corresponds to the bike tour, right? So how do we go about doing it? So we basically try to cluster all of these events based on two properties over here. The first one is we want to capture the geometric similarity or the shape of the event. And to do this, since all of these features, the peaks and valleys, are essentially a subgraph of the given road network of New York City, we look at a graph distance metric, right? Graph similarity. And we also want to capture the topological similarity. So in this case, what we want to do is they have to be topologically equivalent of some sort, and we use the volume. So if you again consider it as a terrain, so the volume of the peak or the volume of the valley, we use that as the topological similarity. I mean, more formally, that's basically the integral of the persistence over the spatial region, So we do this similarity, and then we just cluster them into a set of groups. And for each of these groups, we can also create a key, as in index key for this group, which is basically the average shape and average volume. So this is like so this was between 5 a.m. and 10 a.m., this example, on, okay, I don't remember the date, but it was on Thanksgiving in 2011. And there is this parade that happens near Macy's, the Macy's Thanksgiving parade in New York City. And so you have it, all of these streets are kind of blocked over there for the parade to happen. And so the average of all these shape would be a shape something like this, the ones in dark, right? And this key allows us to do efficient search for similar patterns over the data. So now, given this, I mean, we have a lot of these macro groups. Some of them are interesting, some of them are not. And again, given very large data sets spanning several years, it's very difficult to automatically say that, look, these are what are interesting, these are what are not interesting. So we don't want to do anything automatically. Instead, what we want to do is get the humans in the loop. And in order to get that, you need a good visualization interface that is intuitive, that domain experts can use, and it helps them in understanding the data, right? And to do that, we basically use the properties of macro events to come up with two different visualizations that are hopefully intuitive to the user. So the first one is what we call a timeline view. And here I've shown 4 different examples of macro events. So what are those? So this basically shows that there are 2 micro events that happen on consecutive hours, and that's it. It stops at that, right? So this particular case, you have 2 micro events that happen on consecutive days. So even when you're looking at hourly, it happens for 1 hour, then it happens only the next day at, say, a similar hour. And here you have, say, 2 micro events that occur on consecutive weeks. And here's an example wherein some event occurs every day, for every hour on every day during the week, right? And we sort the events in this view based on the topological property over here. So in this case, the volume potential, right? And once you have this, we have another view which we call the event distribution view, wherein we plot each of these events based on 2 parameters. One is basically the density and the other is range. So if you take this green example over here, it has a range which is 2 hours, right? It has a low range, but the number of micro events that are part of this 2-hour range is 2, right? So there's basically 1 event in every hour, so it has a very high density, which in this case is 1. But if you look at this event over here, it has a very high range, and it also has a very high density, right? These 2, on the other hand, so this event has a high range because it spans over a week, but it has very low density, and similarly, this spans over a day. It has both low density as well as low range. And if you can roughly divide it into 4 quadrants, we are primarily interested in 2 of these quadrants. So basically here, which has very high density. So basically we are interested in high density regions because hopefully that would give us something interesting to look at, right? And this would be like rare events, rare occurrence of these events. So like the fiber or bike tour, it happens just on that 1 day. So it kind of rarely happens, but when it happens, it has high density. Or frequent occurrence of these events. So one example of this would be something like if you look at Penn Station over there in New York, so it is like a transit hub, right? A lot of people go to Penn Station and there's lots of taxis there. And so there is always high number of taxis there throughout the day, irrespective of the time, right? So here you know that there's going to be a peak over there always. So that would be like a frequent event that happens that is potentially interesting. But the main advantage here is that while this again like kind of guides users saying that, okay, look at this quadrant or look at that quadrant, it doesn't remove the other data. Users can always go back and say that I'm not interested in that. Let me focus on see what something over here is, select it, and maybe that's useful to the user, right? And of course, here we are looking at hourly resolution. You can change the resolution of time. So say we move on to a daily resolution, then this particular event would automatically go to this quadrant, and you can again see that, okay, on a daily basis, this is potentially interesting to me, right? Or if I look at weekly, this event that happens just once a week would potentially become interesting, right? Well, all of this is good in theory. Does it actually work when we use real data? And again, we are using the taxi data over here. Right. So here all the experiments we did was with 2 years of data between 2011 and 2012. And this is like all the event groups in October of 2011, and this is like the general shape. You see that there are a few that are kind of interesting, have high density, and most of them are somewhere in this region, right? And say we select this particular lone point over here, lone event group over here, it corresponds to this region over here. So if I zoom in, this particular path, and this is actually, and this happened on October 31st, which was Halloween on that year. And there's a Halloween parade that happens every year at that time, right? So it's kind of very intuitive. By just selecting that, users can quickly get a sense of, okay, what kind of things are happening in the data, right? So instead, let's look at daily, and let's take October again. And let's look at some events that occur, say, for 2 days in a row. And we find 3 such potential events, and let's choose the one that has the highest topological property. And so this corresponds to, I keep forgetting the name of this avenue. It's 4th Avenue, I'm not sure, right? So this is the region where on October 9th, there was a Hispanic Day Parade, and on October 10th, there was a Columbus Day Parade. So you can actually find these, and the user interface actually gives us on what days it occurs, and so you can kind of explore, right? And so here, so for these 2 examples, what we're looking at is a set of minima or the set of valleys. So instead, if we look at the set of peaks and look at frequent events, right? So these would essentially correspond to taxi hotspots, since we're using the taxi data. We basically, oops, messed up my thing. Okay. So if you look at all the taxi hotspots, you would get locations like Penn Station, which I mentioned. There's Port Authority Terminal. Then there's this place called Columbus Circle near somewhere in Midtown over here, which is again a very touristy spot, and a lot of people go there. Right, it's right at the corner of Central Park over here. And you can find all these hotspots of taxis. But what's more interesting is when you filter over time and say, I'm only interested in hotspots, say, towards the night, where taxis are more prominent at night. So we did from 9 p.m. till 6 a.m. And then when you look at it, what you get is you get these different locations, which basically corresponds to where a lot of nightlife happens in New York City. So all of these places has lots of nightclubs and bars, and I think Jorge can confirm that. And again, there's Hell's Kitchen, which again has a lot of restaurants, bars, and so on, right? So you can find all these interesting kind of features. And so I started this work when I was new to New York City when I started working on this, and I didn't know anything about the city. And it was like, by just looking at this taxi data and working on this project, I got to know a lot of interesting information about what was happening in New York and lots of different places and so on, right? So how do we use this? So an example of event-guided exploration would be by using this interface. Say you find this kind of fiber or bike tour, one particular event, the user can then manually go to that time step and kind of explore what's happening on that time step, right? So if you go over there and you look at all the other minima events, you can actually reconstruct the little bike tours path, right? And of course, there is the similarity search that you can do. So you take the bike tour, I have this shape over there with some topological property, and I search. Since I know the property and the shape of this, using the index on all the other event groups, you just have to search. And when we searched over 2 years of data, we actually got these 4 different events that happened. Right? So there was a Dominican Day parade, the Fibero bike tour again on the following year, and Dominican Day parade again on the following year. And there was also this Gaza protest that happened in NYC, apparently around the same location. And yeah, one thing is over here, I'm talking about all these events and I'm giving a name to them. But when you work with the data, you just find these shapes. So what I basically did was then searched on Google to see, okay, what happened in this location during this time? And I could get, okay, this is what happened at that time, right? So this raises actually an interesting question for future, which is, can even the explanations for these different features that we find with the data come from other data sets, right? So this is available as potentially news or pictures tagged with time and some metadata along with it, right? So you have lots of this other data that's floating around on the web. So is there some way we can, or in some cases it could also be by, say, permits given for roadblocks by the city, and that data is again available as open data. So can you somehow kind of get the explanation of a given data from your data? That's an interesting point of research that you can focus on. So another example of search is if you take the expanding date parade and you do a query, and you actually find that that particular street, there's a lot of parades that keeps happening over there over time. So, and one of the advantages of using topology in this case is it's kind of generic. As long as you can convert the data into some sort of a scalar function, and given urban data, which has set of spatio-temporal points, even something like a simple density function, and you just plug it in, and you have a technique to quickly explore data, to get some initial insights into the data by just using topology and proceeding with it, right? So given a new data, we know how we can start understanding the data before going into any fine-grained details, right? So the next question is obviously, you have multiple data sets from the city, and how can we use it to understand the city? So before I go into that, if there are any questions you would like to ask?
So in the previous section, you seem to be looking for things that occur maybe often and frequent in different ways. Another way of something being an event might be if there is some symmetry pattern or some regular repetition. Yeah. Is this useful, or is this more complicated, or it's in the works?
I mean, it is like the kind of events we are interested in is using topology. And of course, there are lots of event detection techniques that are there. You could use any of them. But to answer your question of whether it is useful, I cannot say without looking at it. It might be useful for some data sets, it might not be useful for other data sets, right? And I don't know the answer about the utility of those. I would say potentially everything is useful as an initial step.
I was thinking so even for taxi data, there might be a regular pattern every day that lots of taxis have to go from north to south or south to north New York for some reason. Yeah. So then maybe you could see that.
If you can identify that, yes, it would definitely be useful. So there is, talking about that, there is actually a pattern that happens, which is like, in general, around 4 p.m., between 4 p.m. and 5 p.m., you cannot hail taxis or it's very difficult to hail taxis in New York, right? And yes, again, it's your definition of event and what is happening. You can keep adding more and more details into it to identify different kinds of events and ultimately use a visualization to explore it, right? And yes, each of them is going to give you different answers. It's going to answer a different question that you're looking at. And a lot of these is extremely useful, especially for answering any policy changes that you would want to do. So I think Uber, for example, Uber and Lyft make use of the fact that taxis are really difficult to get between 4 and 5 p.m., that they have this increased rate at that time, always, in New York, right? And so it's things like that. And obviously, I think even the city, the TLC was thinking of, and the reason for that is basically that that is a time when all of them, they change shifts. So people have to go fill up their tanks and drop off their taxis and sign off for the day, and new drivers come in and take the taxi. So I think TLC was also trying to kind of use that information to make other changes and so on. But definitely it would be useful, finding or some sort of symmetry in the data, something that happens frequently and these kind of patterns. Yes.
Is there other question?
I was wondering if you can comment or recommend an efficient way for indexing all this data for example, similarity queries.
Okay, so again, the question is what kind of similarity you're looking at. So if you're looking at this similarity over here, what we have is we have the general shape of, we have subgraphs, right? So you need to search over different indexes. So if you have them in single groups as these are similar, then you could search. It's more like a hierarchical search that you do, or at least what we do in this case. It is like we search for groups which have a very similar shape. And since the number of these groups are much smaller, even a brute force among that, it's like going down a tree. You just search some groups and then fine-grain your search towards much more fine-grained things, right? So it would be something like a spatial index that you would use to do these kind of searches. And I mean, there are different challenges that come in, which I would be briefly mentioning later again, is not just for similar events, even just querying the whole data is not easy. When you have, for example, 5 years of taxi data has something like 860 to 900 million trips that happen. How do you query over this? And Twitter, if you keep getting all the tweets over years, even 2 or 3 years of data has more than 2 billion tweets, which is geotagged. You have a lat long, and you have time when the tweet was done, and you have other text with it. So that poses totally different problems. And yes, you would have to kind of customize your kind of index based on what you want to search, but there is no, one-size-fits-all index that works for everything.
Any other question? Yeah.
Hello, my question is about the first part about the generated topology. For following that process is necessary to reduce the dimensions of the original data, or how you can select some dimensions to generate a merge tree?
Sorry, I didn't hear the first part.
About the merge tree.
Here from the mic. Maybe don't do something.
About the merge tree. Is it necessary to reduce the dimension of the original data, or how can you select what?
Okay, so the merge tree is completed on the CR. So there's one point that I missed out over here is basically converting the taxi data into a scalar function. Right, so you have a data which is a set of points all over the place, and we want it to look something like this.
So maybe the question is because at the beginning you mentioned that for the taxi data you have the space, time, information, and then some more attributes, right? But in this point you are using only the space and time, right?
Space and time, just the points and the density of points. you could always change the whole thing into, say, the fare, right? So the average fare around that region, or the average distance traveled by the taxi in that region. So if you look at the paper, we have another example using the subway data wherein we look at delays in schedule. So there it's a different scalar function. So essentially it's how you compute the scalar function. And at least in this case, the density function over here is, I'll be going into a little more detail about how to compute that next, is something like a group by query in your database, where you want to group by for each of the particular regions of interest, right? So if you're familiar with databases and SQL, so it would be like finding all points that are within these different regions and group by these different regions. So in this case, the region would be maybe a spatial region surrounding each node of the graph, or separate the region corresponding to the pixel.
Okay, we're going to continue because you are going to present another application, right? Okay.
Okay, so now let's talk about how we can understand something about a city from this data, and let's be a little more concrete about what we mean by this. Why would you even want to do this, right? So you have data coming from different cities, and how can you compare the city? So what does the data say about the city, and how can you compare the city corresponding to this? And why is this helpful? So it could be like used for designing public spaces, right? So you understand what works. So for example, New York is a very old city, and based on the data, you see some sort of patterns over there, some things that you know works very well in New York, right? And now you're designing a new city and you want to have similar patterns over here, or you have some city and data and you know a similar public space or whatever, that the infrastructure that's there in New York, somehow it's not working over here. Why is it not working, right? So that way, by looking at different data sets corresponding to those regions in New York and then compare it with this, you can find, say, some differences, and it could potentially help us say, okay, fine, maybe you have lots of tourists flocking into some region, but the number of, shops that are there catering to them is kind of spread out in a very haphazard way, because of which it's not helpful. And you see, let's see how it's done in New York, and let's try to replicate this in the city, right? So you can kind of understand what works, what doesn't work, and help improve the design, right, in another city. And another thing this would also help us is just look at different properties of the city itself. So for example, how do cities behave over different time periods? So how does, say, some part behave during summer versus winter? The trends are going to be totally different in summer, and it's going to be totally different in winter for obvious reasons, depending on the city again, right? So in the equatorial region, it's going to be the same throughout the year potentially. But at least in places that's way north, for example, there's a clear difference in summer and winter and how things work, right? Or how things work on weekdays versus weekends. So this could, again, help kind of plan some changes to policies and things like that. So say maybe there are more tourists on weekends and they flock towards certain places. So maybe I need to improve public transportation or increase the frequency at those times, whereas on weekdays the priority would be elsewhere, right? And our goal to achieve this is using what we call the urban pulse. And here what we are interested in is somehow to capture these trends or patterns and the different frequencies of how things keep changing at different parts of a city, right? So to give you an idea of this, I'll be using the Flickr data. I'm guessing most of you are aware of what Flickr is. And in particular, here we are not going to be using the exact image, but we are just going to look at where the pictures were taken and when and where the pictures were taken, right? So again, there is space and time involved. And say, let's look at the Flickr activity in New York City. And typically, when you look at the general kind of photos taken at 7 a.m., you would have something like this. So here, the domain, we are just converting the city into a general grid, and for each pixel, we define a function value. And here we have normalized it between 0 and 1. Right? So at 7 a.m., you see that there are some parts of the city where there is some activity. It is not very high, but it is still kind of higher than other places. And then when you go to 11 a.m., all of these places, the activity becomes much more prominent, much more kind of significant. And in addition, there are new places where there's some sort of flicker activity that starts to happen, right? And say when you go to 7 p.m., some of the places which had high activity now don't have high activity anymore, but there are new places that pop out wherein there's more activity. So this is kind of interesting. So this is near Brooklyn Bridge, and a lot of people like to take a lot of photos of the Manhattan skyline, and especially during the evening dusk, right, with the lights coming up and things like that. And again, some places like here, this is on East Village, and okay, I forgot the name of this place, Williamsburg. So there's some activity that starts happening, and again, when you look at 11 p.m., again, like Brooklyn Bridge is no more kind of interesting, but if you look at the Williamsburg and even the East Village over here, it becomes much more prominent. And again, the reason is Williamsburg has a lot of nightclubs and it's always active at night, right? So in some way, you can actually capture this flow and ebb of the different activity across different points of the city using just this data. And in this case, we are using Flickr as a proxy for tourist activity, right? And so how can you try to be more concrete about how to define this activity in these locations, right? So what we want to do is somehow capture these locations where this pulse, where this change of trend is actually interesting. So we need some way to define, again, what is interesting. And then we need to quantify the pulse at each of these locations. Once we find these interesting locations, we want to be able to concretely say, okay, this is the pattern followed by the different locations, right? So we want to track this activity that's happening, and we want to, again, be able to do it over multiple temporal resolutions. So for example, you could have, you need to look at, say, for weekdays, weekends would be a different resolution, morning versus night would be a different resolution, right? So you need to be able to do that over different resolutions. So let's look at these two operations and let's see how we do it. The idea is, again, let's use the topology of the data. That's essentially what we are doing here. So say this is my terrain that corresponds to this data, right? And so maybe the peak V1 corresponds to the Natural History Museum over there. V2 would correspond to Times Square. And say V4 corresponds to this Williamsburg area at 7 p.m. when people just start flocking over there. Right? So it's not a very high peak. And again, since we are basically looking at high and low activity here, we are primarily interested in the set of maxima of and the regions corresponding to the maximum. And again, if you look at these features with really high activity, they are really high peaks, and this would be a much lower peak, which is again captured by the notion of persistence that I briefly explained about, right? So we are basically interested in high persistent maxima, and we say that a location is interesting if it has a high persistent maxima, right? And before defining the interesting locations, so again, we need density functions. We need a scalar function, and for this example, I'm going to be using the density function. So this is essentially, like I mentioned a while back, it is like a group by query that you do on a database. So we have a set of all these pixels, the regions corresponding to the pixels, and what I'm saying is find me all points or count of all points within each of these pixels and group by the pixels, right? And you want to group by again the time of day. So there are two group bys over here. One is for each pixel, and for each pixel you want to group by hour, for example. So here we would have for every hour, say between 12 a.m. and 1 a.m., 1 a.m. and 2 a.m., 2 a.m. and 3 a.m., so on. So we kind of aggregate everything together, right? And you could do it for different resolutions, and we currently use 3 resolutions, right? So the other is basically day of week, wherein the group by is based on group by all the days of the week. So this gives us kind of the density on Mondays, Tuesdays, Wednesdays, and so on. And finally, group by the month of the year, right? So this is for each month of the year. So once we get this, we get a set of scalar functions for each of these resolutions over time, and we identify all the maxima of all these scalar functions. So there are going to be a large number of local maxima that are found. And we say a location of a prominent pulse is if that location is a hypersistent maximum in at least one time step, right? So say during the day, for example, Williamsburg region, it becomes hypersistent only at between 10 p.m. and midnight, right? So, but during the rest of the day, it is not interesting. So, but still, since it is hypersistent for at least 1 hour during the day, we say, okay, fine, that location is interesting. And not just time, so maybe a location is not interesting when you consider over the hour of the day, but maybe when you look at the days of the week, you can see that, okay, fine, some locations might have a lot of activity on weekends compared to weekdays, right? So we want, and if so, essentially, if a location is hypersistent in at least one time step, in at least one resolution, we say that location is interesting, or it has a prominent pulse. And using this definition, we find the location of all pulses. All the locations that have a prominent pulse. And once we have this, we then move on to quantifying the pulse. So how do you quantify the pulse? So we need to capture the pattern that happens over there, and we define what we call 3 beats at each of these locations. So the first one is a significant beat, which is simple. It's a 0-1 time series, which basically says, is this location a hypersistent maximum or not, right? So let's take this example again, and if you look at V1 and V2, these 2 peaks are hypersistent, say, at this time period, and therefore it would have one corresponding to that time step. Whereas the others, V3 and V4, even though they are maximum, but they are not hypersistent maximum, they wouldn't contribute to the significant beat. The second is what we call a maxima beat, which is also a 0-1 time series, and which says whether a particular maximum is, or a particular location is a maximum or not. So in this case, you're going to have all 4 of them are going to be have a maximum beat at that particular time step. So the general intuition here is that this kind of captures the kind of trend when that location is prominent on a global scale, when you look at the entire city, and this captures more like the interestingness with respect to a local scale. While globally it might not be all that interesting, but corresponding to just its surrounding neighborhood, somehow that this region has more activity, therefore it's potentially interesting. And the third one is basically the scalar function itself that we compute using the group by query over time, right? So we can normalize, you can normalize this between 0 and 1. So this is a variation of function value at that particular location over time. And here again, we have these 3 different time series for the time of the day. You can repeat it for the day, different resolutions. So you have the same thing for day of the week, and then for month of the year, right? So essentially what it gives us is some sort of a feature vector for each location of the city. And instead of looking at all locations, we just look at locations with a prominence. So this feature vector can essentially be considered as a signature for every location. And the advantage is it's data oblivious. So given any disparate data sets, it allows us to compare different locations based on the signature, right? Or even across cities. So you can now use this kind of signature to rank different locations. You can use it to compare different locations, which could be within a city or across different cities. But again, a common problem is you can have lots of locations when you consider data sets over different time periods, right? And different cities. So in order to, again, identify what is good, what is not good, and get more understanding, we get the human in the loop, and we design this interface, the visual interface, which we call the urban pulse interface, right? So in this example, we are using Flickr data, and then we are using two cities. This is New York City, and this is San Francisco. And the interface consists of this pulse, which actually shows on a map the different pulse locations. And then we have a simple scatter plot, which looks at different time resolutions and gives the rank of each of these pulses along the different time resolutions. And this is like the overall rank along the y-axis. Right? So you can kind of explore the city. You can change, say I want to compare summer versus winter or summer versus summer. You can change the resolution. And everything is linked, so by selecting, you can filter pulses with ranks of interest and look at how the beats vary for each of them and what it corresponds to in the map. You can also filter based on some regions of interest in the map. Say I'm interested in some public space and see how it works. And look at similar regions in San Francisco by filtering and again looking at the temporal beats. And you can also do a search based on the feature vector. So I find these locations and I can query for, give me the closest locations based on this feature vector. And you can again find interesting resolutions, right? So you can actually use this interface to get better understanding of the data. And just so you know, we have the code and everything, the interface, everything is available as open source in BSD. You can find it at this GitHub location. And if you just want to play with the example that we use as part of the paper, you can reproduce whatever results at the following website, right? So again, now the question is, we are doing all this, is it actually useful? Do people actually use it, right? So we collaborated with domain experts while working on this project, and in particular, we worked with architects from this firm called Kohn Pedersen and Fox in New York City. And they are interested a lot in urban planning and understanding different parts of the city and different neighborhoods of the city, right? And so there, for them, they basically use the Flickr data, the taxi data, and I think the subway data to analyze some aspects of different public spaces. And we also collaborated with a scientist who basically works on understanding social interactions and human interactions using Twitter dataset, right? And in particular, in this particular case, he was interested in understanding the cohabitation between different cultural communities. So here what we did was we used Twitter as a proxy for cultural communities, and especially the language in which the tweet was given, right? In the interest of time, I'm just going to give you a couple of use case examples from the architects. So the first one is more like, how can you understand different public spaces? So for those not familiar with New York again, so these are three places in New York that are kind of famous. This is Rockefeller Center, which has a very high tourist crowd. Then there is Union Square, which is almost always crowded, and same Bryant Park, right? And typically when you look at it, people think that all three of them, since it's kind of crowded always, has similar kind of properties and so on. And they expect tourists to like all three of these places in the same way. And right, so they are typically classified as being similar when you look at different things. But when you actually look at the different beats corresponding to these three locations, you see that they are totally different, right? So especially with respect to tourists and Flickr data, which is the proxy for tourists over here. And it's like Rockefeller Center is almost always kind of filled with tourists at any time of the day, any time of the year. And whereas Union Square and Bryant Park, not so much. So it's usually during the evenings in Union Square when there's something interesting, when there are some kind of activities happening over there and people flock around for shopping, especially around that area. But in general, that's not the case. And Bryant Park is almost always not interesting for the tourists at all. Right? And so it's like by looking at it in a much more fine-grained level, you can see these subtle kind of differences between different data sets. And of course, it's like you can also compare regions from one data set to or one city to another city. So again, that's the kind of advantage. New York and San Francisco have totally different shapes. But since we are abstracting everything into just different locations and a feature vector corresponding to this location, it helps us compare and search, right? So if you look at the location in San Francisco that is closest to the Rockefeller Center, it actually corresponds to the Alcatraz Island, which has a very similar tourist property with respect to Flickr data. So to recap, the main takeaway here is that when you have data and when you have really large data, using computational topology to a certain extent, because it kind of abstracts the data away as scalar functions and it's kind of efficient, you can find arbitrary shaped features and use it for analysis to get a first understanding of the data, right? But usually any analysis technique need not be just topology. It could be any of the event detection techniques from machine learning or any other domain. For them to be useful, I would say you cannot be kind of very rigid in saying it's 0 or 1, whether it's not useful or useful. There's always a lot of gray area in between, right? And so visualization really helps in that. And if you can design meaningful visualization to explore this data and get the human in the loop, it's going to increase the effectivity or effectiveness of your technique a lot more, right? And it not only helps guide the users, it also helps handle the scale of the data. Because you're focusing on just certain parts, you could just focus on a subset of the data and keep moving it as the user keeps exploring, right? But this is really not the end. And from my point of view, this is just the beginning, especially when working with urban data sets. So there are numerous data sets. So if you look at New York City alone, the NYC Open Data Portal, there are over 1,300 data sets, and it's just increasing on a weekly basis. And of these, almost over 500 of them are spatio-temporal in nature, right? And each of them have several attributes. On average, there are at least 10 different attributes corresponding to each data. And all of them are really large. So it's large not just horizontally in terms of the number of columns or attributes, it's large even in number of rows or points in each data set, right? And so given this, there are lots of challenges that open up in multiple fields of computer science in general. And so for example, you go into data management, there is the problem of data cleaning. So there's a lot of data that is incorrect. How can you clean the data? Or even as a simple thing as querying, which was even raised earlier, it's like, it's not easy. So you have the taxi data with 800 million trips, and then I have a visualization interface and I want to find, or say even I want to just compute these scalar functions over different time steps. Or I'm just interested in all trips that happen between, say, Manhattan and the airports on weekends, right? So even doing these kind of queries, and if you use existing databases, they are not built for spatial data. They are all built for regular tabular data, and they have been optimized for it. But when it comes to spatial data, each of these queries takes at least a minute, if not hours, when you want to compute these kind of scalar functions, right? So again, the challenge here is how can we design different indexes, querying techniques, and how do you even manage all this data? How do you make them consistent and correct noise, or at least flag noise, and so on? And of course, there are challenges, again, on the analysis side. So here you have, it's like, I focused on using topology to find interesting features which correspond to something like peaks and valleys. right? But there are lots of other techniques, there are lots of other definitions of interestingness that you could potentially use. So what other kind of features can be found? How can you explain features? Now we have huge number of data sets. Can features in one data set be explained from a feature in the other data sets? How does the interaction between different components corresponding to these data sets work? Can we find relationships between these data sets, right? And it gets a lot more complex when you want to handle data in 3D from cities, right? So cities, you have, it's not just plain, just a location, but you have buildings which have height, which have different texture. Some of them are kind of stone buildings. Some of them are much more modern, has glass facades. And so a simple example here is how would sound travel around, and how noisy would the city be during construction. So all of this is kind of affected by the 3D nature, the shape, and the texture and all of these. So just moving from the base 2D to 3D increases the complexity a lot more, and we need efficient algorithms to kind of deal with it, right? And of course, there are challenges in visualization too. Again, it's like how do you interact with spatio-temporal data? It's not static data anymore. We are working with space and time, and it's varying over space and time. Videos help, but it doesn't capture the user's attention, so you need to somehow keep abstracting the data, come up with better visualizations, and again, handling 3D on top of it, right? And this is like kind of the core kind of thing, and all of them are kind of interconnected to each other. You cannot have one without having any advances in the other, and this whole thing together, and you can actually use this and urban data to hopefully make cities much better in the future and improve everything that's happening in cities. Right, so this is essentially the kind of work that we are focusing on in our group here at Dada at NYU. And with that, I would like to say thank you, and we can answer any questions.
So thanks again, Harish, for the great talk. For those of us who've been around for a while, I guess we would, rather than calling this urban big data, we'd just call it GIS. Can you clarify sort of like what, is it just a new name? Is it the same kind of concepts, issues? It's just that now that these data sets are open, I'm trying to figure out what's
they're different.
Yeah.
Right, so GIS, at least in my mind, the way I see people working in GIS, they work more with general, like the network topology. It's actually kind of I don't see the influx of external or new different data sets coming in over there. It's more like it's focused on, what can you say? So you have these road networks. It's potentially purely just 2D. That's a better way of saying that.
Well, I mean, not so you saying potentially.
I mean, it's not terribly different. I mean, it's not different as such. There is a lot of overlap between the two. But here, I think this is more like this is.
It's the same thing. I mean, we yesterday we were talking about deep learning. We were saying, well, okay, if you've been around, it's hard to tell you this.
Right. Yeah, I mean.
Yeah, I'm just.
Well, I'm just trying to think up of some examples of something that's GIS, which is kind of different, but I'm not finding any. So, yeah, in a way, I think this is more focused on just cities and some properties of cities. GIS is in general, even looking at, for example, climate sciences and the simulations that they do over movement of wind or hurricane tracking. Everything falls under GIS, and big window, right? Those particular examples. So you could say this is like one small subset of that, which is focused on just cities and internal to the cities and some examples, particularly to cities. But it also has some different kind of connotations. Example is when we say urban data planning, so one of the works that we are doing, and we did for New York City, again, working with these urban planners and architects, was like, how does shadows affect, how do new towers and new constructions affect shadows in a city, right? I don't think you can classify that as exactly as GIS. It's more like it would move on to computer graphics domain to a certain extent. But it's more like it's looking at how the shadows are kind of accumulated over different time periods, how it affects vegetation, how it affects all the other different properties, right? So you're looking at properties of cities. There is a lot of overlap between GIS and urban science, urban data science, if you can call it that. But I wouldn't say all of urban data science is GIS. Right? Or you're looking at construction of cities themselves, or looking at new towers that kind of help improve the views, or there are cities like London, and wherein you put in a new tower, it shouldn't change the general view of the city, right? You should still be able to see different landmarks. And if you have techniques that look at that, that would still be considered urban science. But I don't think that would be considered GIS. Maybe I'm wrong, but yeah.
That's urban plan. That's not urban data. I agree with you.
No, I would say urban big data, because there are, I mean, New York City, the number of buildings, if you look at just a 3D, the number of buildings are over 100,000.
I understand that that is true, but it's not necessarily big data driven.
It is big data driven because you're looking at shadows over all time steps, that's over the entire year, with the sun movement. It's still, I mean, the big data is again relative. What is big data for immobile is not what big data is for the other. So I think the term here is more like big data, whether, so yeah, it's a philosophical.
A different question. What's the most surprising thing that you actually found? The examples that you've given are all like sanity checks.
Yes.
There are things we already know, and the fact you discovered them is good.
Right.
Validation.
Yes.
The things that we know, it's actually replicated.
Yes, so an example of something that was surprising was when we looked at the subway data. So we have live feeds of subway trains moving around, and then we have their schedules. So one of the things that we did was we collected a lot of these live fields, and then we saw that what is kind of the delay in subway over different stations, right? And we actually found certain, and this was when we actually found certain kind of delays. Again, there are some delays like sanity check, like what happens at the Wall Street station, for example, right? During peak hours, there's always a delay, and we know the reason behind that. People at MTA know the reason behind that. But there are some other stations which are like huge, like this was in downtown Brooklyn and Borough Hall. There were some delays which were like, we thought it was a bug, or I don't know, maybe with the data or something like that. And when we actually showed it to the MTA people over there, some of them thought it was a bug, but there were others who said, no, that actually happens. And so they were kind of, in general, surprised by this happening at those time periods, and they were like, what could be the potential reason? And they started discussion potentially. So we did find some kind of events like those, but I don't know if that would be a good thing to add to a talk, wherein I'm not the expert in that domain, so I cannot answer any questions if that was asked. And so similarly, when, in Urban Pulse, again, using the Twitter and the way the interactions happen, or different languages that are spoken, for some, it was kind of straightforward, but we did find something that was like, I think the way, I don't remember which exact community, the tweets in Italian, I think the way it varies over summer and winter was kind of really surprising, at least to the scientist who was working on that and started looking at it in detail.